Okay, so he has 10 seconds. Good. So it's my pleasure to welcome you today for our second CLSP seminar. Today our speaker is Charles Yang of the Department of Linguistics at Yale University. Charles did his PhD at MIT in the computer science department and finished 2 years ago in doing computational modeling of language acquisition and language change. He's also done some very interesting work on syntax, theoretical syntax, and the formal structure of the grammatical system. And he's one of the very rare individuals who really combines a knowledge of theoretical computer science and models of computational models of learning that is informed by theoretical linguistics. So it's a pleasure to welcome him here today, and he'll be talking about rules and analogy in word learning and word change.
Thanks, Bob. Thanks for having me here. So the advertised title is certainly Rules and Analogy in Learning and Change, but there's a bigger fish to fry. That is, I'll try to say something about the evolution of language, which has become a pretty hot topic nowadays. So I'll try to show that what we learn from studying learning and language learning and change can inform us on how language actually originated. So again, in the evolutionary framework, I'll start with the Darwinian paradox. That's a fact about all languages I know of. A fact is probably true for all languages, that in all languages we have some degree of irregularity. We have irregularities and defaults. In English is obvious, go, went, hold, held, and majority of verbs are regular, going, along, walk, walked. In German plurals, I have 5 classes, and those are irregulars, and this is a default. The reason to show a morpheme or a class as a default is you give the speaker a novel word, then they invariably use ed almost always. They would almost always use ed for English verbs, always add an s for German nouns, and even so, this even extends in a morphological or a lexical domain. So in Chinese and Japanese, they have classifiers. So you say a pig, you use classifier. This is a 1, this is a pig. This is a classifier toad. And this is a goat, which is a different one, but there's also a default, which is ge. That shows up when you give a Chinese speaker a novel word. Kwaku is the first word my son ever produced, derived from truck. And if you give it to a Chinese speaker, they use ge as a default. So the question is, why so? Why do we see this? Why aren't all words regular? It certainly makes a lot more sense from a learning and processing point of view. If everything is regular, learning and processing would be a lot easier, but that's not the case. So that's the problem we're trying to explain. And in the evolutionary framework, a lot of apparent imperfections are due to constraints, a lot of constraints. So Stephen Jay Gould explained, I think, entertainingly, if not entirely convincingly, that pandas have this thumb that is apparently very bad for peeling bamboos, but it's there. So he reasoned that this is actually the byproduct of a vestige of an early, more adaptive evolution. It just got stuck there because there's no way to get rid of it. So that's the route I'm going to pursue. I'm trying to argue there are all kinds of constraints that languages have to obey. And arguably those constraints are actually there before language ever happened. So that's the route I'm going to take. I'll study the ability to learn words by children. I have a competition model of that. And then we'll see if any of these abilities can be grounded in non-linguistic terms. So therefore, if language is considered to be the latest evolutionary product, those abilities would be there before language, and language had to be working with those constraints in order to be usable and to be present in our brains. And the conclusion I'm going to reach is that irregularity is an inevitable consequence of those constraints. Okay, so which takes us to the best known case, certainly best advertised case in lexical learning, which is the past tense debate. I'm going to make a disclaimer here. That is, what I'm going to show you is a bunch of facts from word learning. And I will give you a theoretical interpretation that they are organized by phonological rules. It's not may not be the unique way of interpreting those facts, and I'm not enough of a phonologist to know whether some other ways of doing it, say by constraints, could also work. And frankly, I don't really care. But the point is, I'm going to give you a interpretation based on rules that has a coherent theory of learning and a coherent theory of language change to go with it. And other interpretations are certainly possible, I believe. So there are three facts we're going to explain here. First, in general, both adults and kids add ed to novel verbs. That's known since the 50s. And also, kids make a lot of over-regularization errors. So take, taked, hold it. It's about 10% of all the instances of irregular verbs. And finally, a bit surprisingly, mis-irregularization, the brain-brain errors are very rare, about only 2% of all uses. I thought it was a lot higher, but apparently not. So the target we're going to address is the Pinker's words and rules model that has two components. One is the regular verbs are handled by a rule, namely class D. And the irregular verbs are memorized by association of pairs. So the stem and past tense will be memorized together, and the tradition goes back, the irregular part goes back to Bybee and Sobin and the connections perspective. And it follows a very simple principle that is, the more you hear, the better you memorize. The more irregular forms you hear, you do it, you'll retrieve it better. But this is a simple example, but turned out to be too simple.
Can I ask you a quick clarification question? You said 10%, 0.2%. Can you tell me what it's a percent of? As in
Percent of all uses.
all uses?
Yes.
So when you have 0.2%, is it 0.2% in the sense of all verbs which could be misregularized?
No, altogether.
Altogether. Okay, so, and what fraction of verbs are not regular? I want to renormalize the 0.22. Of those that could be misregularized, what percent are misregularized?
I mean, in principle, every word could be irregularized, right? I mean, why don't I do dent to make an adjective to go length? So in principle, there's everything can be,
Because the example you gave, I think it was bring, right? Bring has
yes.
Bring has this similarity to drink.
Well, I'm going to talk about that. That's the part of the talk is about analogy. So the question is really, suppose to understand the difference between that approach and the one I'm going to suggest is we can look at a simple job of learning numbers. So you're supposed to memorize the number pairs, 2, 4, 3, 4, and so on. Two strategies, and one thing is you can memorize them as pairs, as they are. Right? So that's fine. There's another strategy, which is ultimately what we're going to suggest. That is, we may be able to find patterns among the first between the first number and the second number, and come up with some higher order abstractions, so namely rules. So see, 3, 6, and 7 the second number can be generated by adding 1 to the first one, and 2, 4, 8 can be done by times 2.
Excuse me, these are rules in language, or is this just a sort of an example?
Right, this is an example.
And pairs means just the present and the past?
Yes. Yeah.
So you just memorize it on a list?
Yeah.
I mean, that's the first thing.
That's the first thing. The second thing is to order them in terms of rules or in terms of classes. So that's I'm going to show that's the way we memorize irregular verbs.
Because they are not unique.
Because there are semi-regular processes going on, and there's a model of how to extract that regularity. So this work is inspired by Morris Haddock's suggestion that higher level abstractions or sometimes rules are needed to save space for storage of words. So if things are totally unrelated, yeah, you're going to store them as they are. But if there's any redundancy, a rule can apply to more than one thing, so you achieve some level of efficiency there. Although I probably wouldn't go as far as what Morris would go, where Morris would go by coming up with 10 iterative rules to get all the words right. But the basic idea, I think, is is clear. So the bottom line between this work and, say, Pinker's work is that everybody agrees that irregular verbs must be memorized, somehow, because they're not regular. But the difference is how they're learned and organized and accessed. So that'll be our work. So this leads to the assumption in traditional phonology is the following: that irregular verbs are organized into classes. This is something you find even if you open up a dictionary. The following verbs undergo this changing in past tense, and this goes, the tradition goes way back. So, for example, feed and shoot would fall under the rule of shortening the vowel. This is a very general process, and so on. All that. So the problem is, you have a verb, you have a bunch of rules. You want to make association between them. So when the special rule fails, those are special rules for irregular verbs. A default rule kicks in, which will give you hold it. So we agree with Pinker on that one side of the story, namely all the irregulars are inflected by a rule, but the difference is how do we account for the behavior of irregular verbs. So this is how it works. So you have a verb, irregular verb. To use it correctly, you first must be able to associate the verb with the rule. I'm putting aside the question how those rules get there, and that's the second part of the talk. And the second part is that, can someone switch the lights off, at least in the front row? This is probably very hard to see. All right, we got it.
I can see all the.
Okay. Oh, if you can, I can't. Okay. So there's a second stage where a rule, irregular rule, has to compete against the default rule. So this is really a two-stage process. For theory like Pinker's, it doesn't have rules for irregular verbs. This is going to be one thing. So this means that if the probability of a word, if a verb fails to be associated with a rule altogether, then the default rule kicks in. Or if it has been associated with the right rule, but the right rule fails to apply over the default, you also get hold. So the probability of a word used correctly would be correlated with this frequency times this frequency, straightforward. And this gets interesting because this association is strengthened upon seeing this word, right? So the more you see, the stronger this link is. But this link is strengthened upon seeing every instance of this rule. So simply the correlation would be the frequency of the verb times the sum of the frequencies of all the verbs under this class.
I don't understand. What is the rule R? I mean,
Say,
how do we know this rule R, which doesn't apply, in fact, should apply? I mean,
I'll come back to that. There's an algorithm that
there is what?
There's an algorithm that learns these rules and knows what kind of verbs these rules can apply to.
So there is something characteristic about the morphology of the verb be, which attracts it to rule R,
Right.
which is a false attraction then.
If you want to put it that way, sure. Yeah.
And the default applied at that stage may be correct. I mean, in the example you're giving, hold it, of course, is wrong, but
it's right,
but it could be correct.
Yes, it could be correct.
In other words, the default could be correct because it's correct to start with, or because the morphology tells me to go to the rule.
The morphology tells you to go to a more specific rule first, and then look at the more general rule. And that's why this is the Ellsberg condition in linguistics. The difference here is that the irregular rule overriding the regular rule is a probabilistic process rather than an absolute process. Yeah.
Well, why when you take the probability, don't you have to do the probability over all the different possible R's?
Yes, so you're saying a verb may be linked to to a wrong rule.
Yeah, I mean, you
Yeah.
don't have a magic oracle
Yes.
that gives you the right R, so.
Right. Empirically,
The
that doesn't
probability
happen.
of getting it correct
Right.
means the probability of picking the right R.
Right. The kids are awfully good at picking the right R. Remember, we have this.
So this is probability given that you have the right R.
Yeah. Yes. Yes. So we're gonna in a second. I'll tell you how those R's are. Remember, you've seen here the probability of using a wrong rule for a verb is extremely low. So we'll come to that. So this is a probabilistic interpretation of how different rules may compete to apply to a particular
You're
word.
saying what FB and FR,
FV is the frequency of this verb,
the particular verb?
right? And FR is the sum of the frequencies of all verbs that that belongs to this rule. Yeah. This leads to a two very straightforward predictions. So if you have two verbs in the same class, then the frequency will determine learning performance because they share the same. They share the same second factor. Whereas if two rules are of comparable frequency but they are in different classes, then the size of the class will determine how well the verbs are used. Is this clear? All right. So to show this, we taken all the child data are taken from gigantic monograph by Gary Marcus and Painter and some their colleagues. Look at 4 kids, so all the data are theirs, and so Adam, Eve, Sarah, and Abe. And there's some variation. In particular, Abe is bad compared to the other 3 kids, but they're not bad in random ways. And Abe is systematically bad. It's not some verbs are particularly bad, dragging the frequency down. And the frequency of irregular past tense are extracted from the sentences those 4 kids heard, recorded in the child's database. And the frequency, remember here, we were really comparing, which is bigger, which is smaller. And so relative frequency is going to be sufficient. And the frequency of irregular verbs we got from the database actually don't differ so much from, say, the Brown corpus, because those are pretty often used verbs. Yes?
Sorry, I've had a hard time understanding. So the first line, what does the first one mean if B1, B2?
If the 2 verbs are in the same class, then the verb that's heard more frequently is going to be used better.
Same class means the same irregular rule applies?
Yes.
The same irregular rule does apply or might apply?
Does apply.
Okay, so the verb bold, as in to make something in boldface, which has the past tense bolded, does not go to the same R as the verb hold?
Yes.
It does not?
Does not.
Okay.
Okay, so
Okay, so I'm sorry, I'm still trying to understand. So, okay, so if 2 verbs are in this have the same rule applied to them, then the frequency
individual frequency. If two verbs are in the same class, then this factor is going to be the same for both of them. So the first factor is going to be the only determining factor, only factor in determining their performance.
So how does class size come into?
The class size, what? If they're in the same class, they have the same class size, right?
Yeah.
But if you're in different classes, so despite the 2 verbs that may be of the same frequency, the verb in a bigger class is going to be used better because the second factor is bigger.
And when you say frequency, are you saying just how often you see the verb or how often you see it in the past tense?
You heard in past tense.
Okay, it's properly
Yeah.
written in
Yes.
So this is saying, so these predictions are basically setting up a situation where you can say, okay, there are these 2 separate facts, but it's not necessarily saying anything about the combination. So before in the previous diagram, it suggests that maybe it's some kind of a multiplicative combination effect, but here you're not making any claim. So.
Well, I'm assuming those two levels, those 2 things to be independent.
Sorry?
I'm assuming those two steps are independent. So that's why we do this product.
Oh, right, but I mean, they don't have to be. Doesn't have to be a product.
No, doesn't have, but but something along the line of some some factor of the class size has to be
Monotonic
right.
and both.
Yeah, because this rule is strengthened whenever you hear an instance of opposite number. This is certainly the simplest thing you can do, and it seems correct as you'll see. So let's look at the first prediction, namely you keep words in the same class, and you look at their in performance. So we have some other classes like here given again from by traditional phonology. So you have loose and loose lost is used 98% correctly as heard 63 times in over 100,000 sentences, and that is 95, 53. So the yellow is the frequency,
Excuse
and
me, what are we claiming about leave and lose, that it's in the same class?
they're in the same class, yes. You add
Which is which class?
which is you add a suffix t and then you shorten the vowel. So vowel shortening is a very robust process in the English language.
I'm sorry, it must be some phonological rule, but why is shortened long e and e? Why isn't the shortened long e and e?
Well,
Why isn't leave
right. This
lift
is
rather than leave
right.
left?
This is probably a misnomer, but this is the traditional term from phonology that it's an automatic thing. Once you put a like nation national, reduce reduction, those sort of things are pretty automatic from the English point of view. They're just,
So going from long e to an e is called vowel shortening.
yes.
Even though it's also lower.
It's all yeah. It's also
It's a
it's
set of
also
regular correspondences that arose in the history of English. It's called the Great Vowel Shift, and they are just part of synchronic phonology as well. So people seem to know that those are the correspondences. So, when you say minority, you can say minority or minority. So you know that E and I are sort of equivalent except for length. So you have those correspondences just built into the synchronic phonology of English, but it arose, it's a sort of a historical thing.
Right. And those things have to be altogether referred to as vowel shortening in phonology. So so you look at those frequencies and performance correlations. They're overwhelmingly true, with the exception of this class. So cod is heard 36 times, but used 93% correct. But thought is heard a lot more often, but used actually worse.
So I'm sorry to be so dense. And on the second one, that's again all the same class?
Yes.
In other words, catch and think are in the
Same class, yes.
Because?
Because you do the same process. You change the rhyme to all, and then add a t, then you change the rhyme to all.
But how would I know it from the present tense? Unless I knew already that catch goes to caught, which seems to me this pair thing. How would I compute from that just catch that it's the same thing as think?
Well, that's the point of the rules. The rules and words association are by force. There's no rhyme or reason. You hear something, you hear a rule, you put the two
So the
things
rule
together.
is not a
That's it.
computational rule.
No.
The rule doesn't associate with the pattern.
Right, it doesn't necessarily associate with the pattern.
It
It could associate with the pattern, but it doesn't necessarily. It doesn't have to be.
The rule doesn't make reference to the vowel of the present. It just tells you whatever that vowel was, it becomes all.
Right. Whatever the vowel. Those are rules can be learned. Like a program that can actually learn these
Okay, so
rules.
some rules do refer, so vowel shortening shortens the vowel of the present.
Right.
It tells you
This rule doesn't
Right.
care about that.
Right.
It's just that it's rule 73 for think.
Exactly.
It just
and
makes
then
all
also
out,
rule
Right.
73.
it makes
Exactly.
all of whatever vowel you
Right.
want.
Exactly. Yeah. It just rule 73. There's no reason for this.
Okay,
Maybe-
that's still a rule. That's
Right, right. There may be a reason for it, but there's probably historical reason for those rules, but that's not something the learner has access to. And the exception is the first class that thought is used worse despite being heard more often. That's actually not so surprising because Abe, who's actually overwhelmingly bad, happens to use a lot of thinked than the other kids. So if you factor this out, you see this correlation is still perfect. So this shows that you get virtually perfect correlation between frequency and performance only if you break things into classes. You can go through this yourself, or I can give you a copy of this. But of course frequency is something people look at have looked at in some details, and they found, Pinker and Marcus found, there's correlation of 0.7. So it's a pretty strong correlation, but by no means perfect. But here, once you break things down into classes, you get a virtually perfect.
When you say perfect, you mean by rank order?
What?
When you say perfect, you mean by rank order, or it's really a
Yes.
linear?
It's not. I didn't look at it whether it's linear or not, but it's certainly rank orders.
You might predict that within class. I mean, given your multiplicative
Yes,
model,
yes.
you might predict in fact.
Right. I mean, the reason I didn't give you all irregular verbs is for a lot of irregular verbs, all 4 kids use like twice or something, so you can't really count on that type of data. But in principle, you take a large enough sample of child data, you can do it. I'm going to stick to the to the prediction that two verbs in the same class is the performance is exclusively determined by frequency.
Excuse me, is there any other reason than this one to think that catch, think, bring, and buy are in the same class? Is there any other reason? I mean, do they behave, this set of 4 words, do they behave in the similar way in some
Other
other
than what? What you said other, what's
Well, this is one reason that you put them
Do you mean
in
other-
So you want motivation?
you get the odd ending there. But is there any other phenomenon in language which will put these 4 and not others in the same class?
There are some rules that you can.
His argument is that there is a description that puts them in the same class, and that classification is confirmed by the acquisition evidence. So it's not
Yes.
I see.
Yeah. And there are there is a algorithm that learns exactly
There
this
is
type of
what?
rules. There is a learning model that learns exactly those rules, which I'll talk about in a second.
These frequencies are the frequencies of the child's speech, right?
No, the frequency of adult speech, the frequency of verbs that kids heard.
Okay.
So that's their input
Because
evidence.
this is not from the child is.
It is from
Okay.
the child itself.
Well, it's child-directed speech.
Right, child-directed
Football.
speech. Yes.
Do people think that children get this correct because they happen to know all of those words belong to the same class? Or does the child have some instinct that buy is in the same class as catch?
Well,
I mean,
I don't know. I guess I can't read their minds, but that's what they're. This is what they're.
That's the kind.
Yeah, that's the kind of behavior they show.
Although there might be conditioning on the surface formation.
Right.
Right. Right. You're saying right.
Pronouncing odd,
Yeah.
and so they back off and use a different rule. Think about it.
And this is certainly the behavioral data. And we'll see actually this frequency performance correlation completely breaks down when you look at verbs that belong to different classes. So a verb, two verbs may be of comparable frequency, but if a verb belongs to a bigger class, then it's predicted to be used better. So here we have two classes and some verbs, and hurt, cuts, draw, blow, grow, fly. Again, this is fly doesn't look anything like grow or blow, but they're in the same class. The difference, those 6 verbs have very comparable frequency, all very low, but you see the first class we use a lot better than the second. This is a mystery under a frequency-based learning model. And second, we actually have higher performance despite a lower frequency. So here you have, again, 2 classes. So hertz, cuts are used 80% incorrectly. The other 2 verbs, know and no new, throw, through, were used more frequently but actually used worse by kids. And finally,
what do you conclude from that?
it's a rule that changes the rhyme, the last part of the verb to me.
Why is this rule badly learned?
Why is this rule? I mean,
Why do they learn? I take 49% to be the correct performance.
yes.
Okay.
Yes.
So why knowing that new and through?
That's the rest of the talk, right?
Right. That's what I'm talking about.
He laid out some, overall regularity.
Yes.
If you classify them in such a way, you make a certain prediction. It's largely correct. But now he's noting that there are some discrepancies. And then he's going to tell us why there are those.
And yeah, and right, I guess I'll come back to how rules are learned later on. And also, you got lower frequency despite higher, lower performance despite higher frequency. So you look at the child A. So again, this class, the no change class, is actually used, not great, but actually better than Go went. So the kid actually said Go gold 36% of times, whereas same like come came, which is also very frequent one, is actually used come. 78, I guess 74% of the time, much lower than far less frequent verbs. Because this is again a mystery.
Isn't that A simply nasty?
No, he's not simply nasty. I believe he's the son of a well-known linguist.
Why the hurt and cut group are in two different categories. Hurt and cut have higher performance despite lower frequency.
Right.
Is that right? Okay.
Yes.
I know what your story's going to be about.
Well, yeah. This is only for Abe, because Abe is overall worse than the other three kids.
Well, Abe is worse.
Right. So therefore, you got a lower comp here.
But it's also true on number 2.
Right.
Cut perform better
Right.
than no.
Right. So this class is consistently better than all the.
Okay. So the point about 3 is go when.
Right. It's go in. Most kids did go in fine, but not Abe.
So you're saying that if we weren't convinced by 58 and 51 of no throw,
I'm
there is
sorry?
no doubt with 550 of go, and in other words, here the difference is even larger.
Right. Yeah.
And
Yeah.
even then it's worse, although
Right.
it's just for one child. It's
Right.
even worse.
It's a considerable problem for a frequency-based model. The reason is, again, if they're in the same class, they have this, what I call free rider effect, because the rule gets strengthened, so all the members of the rule get carried along. So this no change class turned out to be a huge class. It's over 3,000 occurrences, things like put or things are set, or letter or something. Whereas this class is much lower.
But,
Obviously, yeah.
but that doesn't answer what happened to go.
Yeah, well, 3,000, is greater than 557, right?
Oh, okay.
And finally, we have again, this is the problem is a simple model of learning that doesn't take into account of other factors in the language, because here's the effect of phonological regularities in the English language. So we may have a case where a rare verb may be used fairly well if it falls under a general phonological process in a target the language. Then that process is vowel shortening. So here are all the vowel shortening verbs in English: lose, lost, leave, left, say, said, shoot, shot, bite, bit. These are the frequencies. Very different. So some very low, some very high, but they all used very well. Okay, so this is, as I said earlier, vowel shortening is a very general process in the English language. I mean, the phonologists should certainly know this better. There are different ways of accounting for this fact, and essentially, when you add a suffix to in general, you add a suffix to a stem, it shortens the vowel. So some examples are given here. This is being argued to follow from some language particular things and some universal things about the language. So again, this is not a fact that can be explained under a frequency-based story. Okay, summary so far. So I've given you some evidence that words are indeed learned and organized in classes. I haven't told you how those classes are formed. That's the later part of the talk. So if a theory would have to explain these systematic patterns, however tools you choose to use, and to me the simplest way is to say that there are rules as in traditional linguistics. And the other thing is, of course, when irregular rule fails, the default rule kicks in, and kids almost never use the wrong rule. So a V going to the wrong R is virtually impossible. And certainly they don't suggest anything like prototypes you've heard in some theories. They're actually rather the rules and probabilistic association between words and rules, and also probabilistic application of rules, or a special rule over the default rule. And certainly there raises the important question of how far can this rule-based approach go? And certainly it saves memory, but it also adds a cost to online computation. Right? So there's got to be, I think there's got to be a balance, because rules and computation aren't free either. That's why I'm a little skeptical about some work in phonology where it tries to compress all the irregular verbs with two rules. I don't think, at least I haven't seen psychological evidence showing that's the case, but there could be. I don't know. But all the rules I've been describing are pretty, surfacey type of rules, and they raise some questions. First, how are those rules learned? I mean, they seem to be there early on. I say this because kids don't deviate from the rules, randomly. Even when they make errors, they don't say hold. They don't say hold, hush or something. So it's like their phonology is organized in some ways, and it seems that they even they make mistake, they follow some existing patterns in the language. And also, what's the status of this default rule? What do we mean by a specific rule applies over a more general one? So I'm going to show you that the rules can actually be learned from application of a general learning algorithm. This is based on the work of Jerry Sussman and Ken Yip at MIT, and picked up by a student of ours recently who did a thesis on this. And some work is being extended to other languages using this algorithm. The idea is that there are learning algorithms that seem to be domain neutral, but it can be used to language, which is a domain specific thing. And this is the approach to language learning I've been pursuing for a few years. This is a case of it. So how do we learn rules? Representations. In the Sussman-Yip model, the words are broken down into segments, and segments are represented by their features, in distinctive features or articulatory gestures, as in some other conception of the primitives of phonology, or really space. You can really some kind of discrete combinatorial representation of things. So apple, PL, apples. Okay. So learning happens like this. Okay. So here's the key part of this learning model. So suppose you start out with nothing, and you hear one word, okay? You make that a rule, okay? And then you hear another word, you make that a rule as well. And then you try to collapse their similarities, okay? So one thing you can do is back here, instead of putting 0 or 1, if you see in this position, so if two words undergo the same process, and the value is 1 here in one word, but 0 in the other one, you put a star there. You see, I don't care, because that feature doesn't seem to matter. So something like this, your schematic, you have. Here's how you learn the default rule very crudely. You see, here walk and walked and talked. They have the same process. They all add d. So you collapse their differences and replace the first segment by a star. You don't care. And then you have racked. So of course you have to modify the rule further. So this star k plus ed is going to supersede all the individual rules. And you do this, for words as they come in, and in the end you get a rule that says star plus d. So that's the default rule. So this rule is actually generalized the descriptive coverage of individual words, and there are phonological changes. So here's actually the rules they've learned. This is this is the result of Sussman and Yip's paper, which I think hasn't got enough attention in the cognitive science and computational linguistics field. So they learned some rules that, if you look at the rules, it says, if the last segment is plus voice and plus sonorant, you add it. But it's not a D, you add a D. Okay, again, the rules are applied in more or even in regular rules, there are more specific ones there, and there are default ones. And the irregular rules are run like this: don't care, I go to add followed by ng. Okay, and add goes to the schwa, and in the context of don't care t. Okay, and this is something they've done and has been duplicated on a number of occasions. So this is the chart of how many examples of regular verbs the learner sees before he reaches the right rule. You can see in this model, it got there actually in about 50 irregular verbs. Whereas this is a model by Mooney and Karloff, which is an inductive logic programming learning model. This is a Ling and Marinoff. That's a decision tree model, and this is a connections model. Okay, so you see, it certainly learns much faster than all the other models, and this model actually eventually gets the right rule, and those two models don't even get the right rule, never. So that's a big problem with connections.
Is this measured on training data?
Huh?
Is this measured on training data?
This is based on what? Training data?
Yeah.
What kind of training data?
Well, I don't know. It looks
Is
like
it
you're
measured
getting-
on training data?
It looks
Did
like
you
you're
test
getting
on the training data or on a
accuracy.
different, on a test set?
Did you
Not
test
yet.
set? Yeah.
What?
Well, here you just simply see what the rule is, right? I mean, if the rule hasn't got to star plus ed, then you haven't learned it. So if the system space out star ed, then you know if you learned it.
It's unsupervised,
Right.
so it's okay to use training data. The
Okay.
question is what fraction of the correct rules were recovered, but you never saw them in training. You just saw it in training.
You just present a system with a sequence of irregularized, regular verbs, and this is the pattern it pulls out. It reaches the conclusion that all those verbs can be captured by a rule star ed in about, on average, 50 examples.
But what? Okay.
And the other models, in particular, this model and the connection model, never gets that.
But it seems like you could build any self-organizing model large enough to capture all the phenomena
Well,
you're
do it.
interested in.
Well, I mean, that's do it. Right? This is a
But
very
then you want to
simple.
see how it generalizes.
What? What do you mean it's not?
Okay, I'm sorry, I just don't understand.
All right. So this is also poses I think the first real solution to the German plural problem, where in German the default class is actually the numerical minority, but here, since the rules are actually some sort of high order description of coverage of its scope, this is actually I believe it's quite possible to learn the default rule star S in German in particular, based on a few number of examples. And this hasn't been done yet.
I'm just trying to see if I'm understanding there. So are you saying that the critical ingredient, the critical factor in making the default rule, inquiring correctly the default rule, is the heterogeneity of the cases? There's no generalization over the stems, so it becomes, is that the factor?
Yes,
Okay.
yeah.
So but is that what Bybee calls an open schema? And I think that's the argument that she gives as a rebuttal of the Marcus.
Well, I guess the crucial thing here is, yeah, I mean, that's all.
That's the point. That's
Right.
the point she makes as a rebuttal. When we were talking earlier, you thought that was unconvincing, but that's the argument you're giving here.
But that's, well, okay, okay, so she's right.
So she's right.
Right. So, okay, I don't remember when I read her paper, but I wasn't convinced at the time. But that's what she says. But that's the traditional view in phonology, right? The default rule just is by definition applies to everything, so it's wide open. I guess there. I mean, yeah. Okay, so So I think the generalization learning algorithm I stated earlier is probably a domain neutral one. You see similarities in representations, you collapse them. So for example, if it rains the ground wet, or if it snows the ground wet, you may collapse the difference by saying, okay, if things fall off the sky, the ground's wet. Of course, we're going to run into more examples and compounding examples, but that's something can, in principle, apply to non-linguistic domains. And similarly, in machine learning, you have the version space learning model where you have hypothesis, more general hypothesis, more specific hypothesis, and try to meet in the middle. Yeah?
I mean, it seems like you've just kind of switched the problem around. Now it's generating a feature set which is appropriate to the problem. So the problem, I mean,
Exactly.
so it's general,
Yeah.
only if you have the right feature
Right,
set.
and only if you have the right representation. The representation, is a language here. Yeah. And they think of the feature representation of, sound is not a hugely controversial issue in phonology.
But also like the same criterion that Hayes and Albright are using in their learning algorithm for morphology, the work they're doing at UCLA, that he actually talked about that here last year.
Okay.
It's kind of similar. So
Okay.
the idea would be that you formulate the rule and you do this minimal generalization. You only generalize if you're forced to. So it's the same
Okay.
criterion.
Okay. Well, I should look it up. And also, we're going to return to the issue of default. Why is default such a big deal? And I believe Ellsworth conditions also domain neutral as well. In conversations, I give you some examples. There's a Gracian axiom that has to be more specific. So if we say this is a lab or simply does language research, it's quite appropriate. If you see a lab that does research, which is technically correct, but not very terribly informative. And certainly in card games, this is 3 aces and 2 kings, we call it a full house, although it's still technically 2 pairs. And in soccer games, if one hands the ball, it's a free kick, but if hand the ball in penalty area, it's a penalty kick. So if someone hands the ball in penalty area, rule B, the more specific one would apply, although the rule A is still technically right. And finally, in phonology, the more specific rule applies. So for lose and the past tense of lose, there's a particular rule says you add T and shorten the vowel, which is more specific than add D, which applies to all verbs. So rule A wins out. And certainly in the learning model, the default rule is the one that contains more stars than others. So the learner doesn't have to store explicitly the default rule. You simply go down the list and see whichever that fits your description, and if nothing does, then the default is going to pick it up. So there's a hierarchy, but the default doesn't have to be represented in any special fashion. Okay, now I'm going to go to this last part of the talk, which is how words change over time. So we see earlier a verb is associated with this target rule, and also can fall through the cracks and go to the default. And also there's a small probability that it'll go to a different rule, like in the brain case. We know that's quite rare, so this arrow is much thinner. Certainly, if all words are reliably associated with the target rule, then language will never change. That's not the case. But verbs or words in general do shift around, and they shift around by analogy. So there's some terms here. So analogical leveling, a special verb can become a default. So strived-strove is now it becomes strived-stroved. This is at least the example they give in historical linguistics textbooks. And an analogical extension, a verb that may be regular can be stuck into an irregular rule over time. So where was where, and now is where war. Okay, and
what's
that
the analogy of the strive? Just analogy to what?
To let's see. Well, it's an analogy into nothing. Therefore, it's an analogy to the default rule. But here it's an analogy where to tier tor or something.
To tier tor.
Right. To tier tor. Yeah. So an analogy does bear gore or something. Yeah. analogy does have effect over time. And remember, a verb can go to its, will be used, will fall under will be used correctly if it's a frequency, somehow a product of the frequency of itself and the size of its class. So that is, you can stay irregular either by the virtue of your very own frequency or by the virtue of the class size. So those two factors are important, but that argues against that only frequent verbs alone can be irregular without taking into account of the effect of class size. So there are some facts here that people have to deal with. In English, again, one huge default class, small number of small high-frequency irregular classes. And German's actually quite interesting. 5 classes, all of significant sizes, and 4 irregular ones, and the default class S is actually the smallest. So again, that's so as you can see, a frequency-based story can be true for both English and German. So that leads to a computational model of sound change.
Can you say that again?
English.
So let me see if I understand. So English, you've got this big default, so
right.
That's frequent. But this actually doesn't say anything about the defaults. What it says is that the irregulars have to be either
have to be very
frequent.
frequent.
Have to be frequent. And what you said is English has a bunch of high frequency irregular classes.
Right.
Are the individual members of those classes also highly frequent?
Yeah. So you have to say be on the top, say, 2 or 5% of according to the frequency-based story, you have to be in the top 3 or 5% of most frequent verbs to stay irregular.
So that's compatible with Pinker and Bach.
Right, that's compatible. But in German, you don't. That the cutoff point is going to be a lot lower. So something can be very infrequent, but by the virtue of being in a very large one of the 4 irregular classes, it can still stay irregular.
Just because most things are
Yeah.
irregular.
Yeah.
In this funny sense of irregular.
Yes. So this leads to a computational model of sound change. This is really just a simulation. So we start with a random set of words, and each of them with a phonological shape, say just 100 bits of zeros and ones. Okay, and so that's the input, and an arbitrary modification of the input to get an output. Remember, in the learning model, if 2 words undergo the same changes, they're in the same class by definition. So you can just group words with identical output rules or processes into a rule by generalization we saw earlier. Then for each word, there's a probability inversely correlated to its own frequency times the size of its class. If you're greater than that, you can toss a coin, or generate a random number. If it's greater than that, if it's smaller than that, you can stay, where you are. You can stay irregular. Otherwise, the word is going to undergo a mutation or an analogy, and be associated with some other rule. And after that, because once you take a word out of the class, you have to make changes to that rule. But if you add a word to a rule, you have to generalize it. That rule. So you adjust the rules, and so this is one generation of learning, and you go and repeat. So I'm assuming rather arbitrarily an exponential decay of analogy probability. Okay, so again, capture the fact that only, at least in English, or the product of the 2 factors, it follows under this kind of curve. If you're high, you can stay there, but if you're low, you get sucked into you lose your spectral status pretty rapidly. And I'm assuming a Zipf distribution of word frequencies. So just to give you an example, suppose we have 5 words, and generation 1, these 3 are in rule 1, and rule 2 has 3 and 4. And you collapse zeros and ones with stars. You got 0 star star, 0 star, and there. And if in generation 2, if word 2 mutates into rule 2, happens that the rules don't have to be changed. Whereas in generation 3, word 3 mutates into rule 1, the rules have to be updated here. Okay, so you remove that. You replace the start with the 1 there. So the decay constant is something you can estimate. I'm not sure so accurately from the frequency of English verbs and their histories. There are some known verbs that were irregular, but not regular anymore. But not irregular anymore. You can take a frequency chart and see where you want to draw the cutoff point. I mean, that's something that in principle can be done. So here's a simulation of 500 words. You start out with 50 classes with 10 class. Every class has 10 words, and you do this learning, and you stabilize to 5 classes. I'll show you in a second what those 5 classes are. And if you use the same decay constant on the frequency-based model, very soon you go to go down to 1 class. Everything is regular. So the frequency store is not only incorrect synchronically, but also incorrect from a diachronic point of view. And so here are when things don't change anymore, those are the rules. Instead of using star, I'm using a 2 because it's simply easier to program. We have one rule that has stars across the board. And we have some special rules. So here's 1, here's 0, here's 0. So those are sub-regular rules that if if the word happens to have 1, 0 and 0 here, and we don't care about all the other bits, it can be a principal, in principle, a member of this class. So what we get here is many of the original rules disappeared. We started out with 50 rules, now we only have 5, and certainly in the process, a lot of them were added when you modify rules and to be more general or more specific, and they disappeared as well. And one rule became the default, the one there, and there are 5 irregular rules containing relatively high frequency words. I didn't report the frequency here, but they're all pretty high. So there's a couple of directions, a few directions that can take this work. We can simulate the effect of a loan word, namely an entirely foreign word, by randomly flipping bits in a word. So something that's not compatible, in general, aren't expected to be compatible with your language. And I suspect that's what happens to German. The default class turned out to, as German speakers tell me, turn out to be mostly loan words. So it's quite possible that some foreign words came in, doesn't fit into this own, doesn't fit into the existing 4 irregular classes. It gets to be on its own. Then a few of them come in, and very soon you get your class sort of features and get a star S. And there you can even, in the fantasy world at least, you can simulate systematic effects of changes in phonology, say the great vowel shift Luigi referred to earlier. You can flip some bits in all words, so some systematic changes have happened, and see what happens. And it's possible to get multiple default rules in areas of the lexicon. So that seems to be the case. You can certainly have, say, all the words. Let's say imagine all the words that starts with an A has a default rule, and all the words that start with a B has another default rule. And in those two groups, you may have more irregular rules. So the default doesn't have to be unique. And certainly you can do richer phonological representations. It's a very good paper by Eric Ristard, but as far as I know, it's never been extended. And to consider the role of phonotactics, this is just to enrich the model for learning. And this can be extended to morphological change, say the change of case, and also to extend to the learning and change of semantic domains. So the classifiers in languages are in general conditioned on semantics. So there's a good deal of acquisition and also historical work on the nature of classifiers as well. Finally, the big fish to fry. What does this mean to evolution? If rule learning and computation are not language specific, but general to cognition, as I've argued, learning seems to be good domain general, and also elsewhere conditions seem to be domain general, then the ability to learn rules maybe a constraint that shapes the outcome of language evolution. Language, whatever mutation or what have you, had to work with those general cognitive constraints. So in order for rule learning to be applicable, evolution must have supplied some appropriate combinatorial representations like you saw in the feature things. It can be distinctive features, it can be gestures in articulation, as my colleague Lois Goldstein has been suggesting, motor movements, decomposition of semantic space, whatever. And there's something being referred to as a particulate principle. It says that basically when something gets complicated, a combinatorial system is inevitable. It's been suggested by Michael Kennedy and in some recent work. But this still means that the learner must be able to perform abstract symbolic manipulations, as we saw in the rule learning case. And also, in addition, probabilistic learning, association, and learning rule applications. So, just to wrap things up, so if rules, I'm sorry, I forgot. The reason we have a default is probably quite like the German cases. You don't, since language communities talk to each other all the time, it's very often to get, it's very common to get foreign words. Once the foreign word comes in, if it doesn't fit into the existing phonology, is going to undergo some changes. One of the things to do is to put them in a garbage can, the default rule. Phonology of words are learned and organized in classes or rules. And this is a crucial break from traditional phonology. I'm saying word and rules association are probabilistic. In traditional phonology, it says, you have a word, you have a rule, apply it. That's it. So that's I think, empirically incorrect as well. The algorithm for rule learning and use seem to be domain general. Struggling learning back may explain the emergence of some classes, irregularity and regularity. And analogy is extremely weak in learning, in synchronic learning. But cumulative strong in history, I think analogy is probably the other than systematic changes like the vowel shift, probably responsible for most of the sound changes in languages. And finally, analogy necessarily leads to irregularity. So if language had to work with rule-based and analogical learning, then the imperfection in irregular verbs would be a necessity, no longer a paradox. So I'll stop here. Thanks.
So I have a question and a comment. First, were the children consistent? Were they making the mistakes consistently in this corpus? Because to me it seems that the context is very important. Like I caught a cold, and I know, I can say I catched a mouse. And some things are just memorized. I'm a non-native English speaker, and to me, I don't seem to work on rules. I work more on analogy. So I have some of the things memorized, and many times I just make analogy to something else. And if the context is good enough to make one kind of analogy, then I will make that kind of analogy.
Right. Well,
and in another context, I might just take the general rule and the default.
Well, that's my intuition too, but my intuition turned out to be wrong. I thought I would learn words by analogy as well, but if you look at the data, that doesn't seem to be the case. So take the word like think. Analogy, by analogy, kids would say think, thank. So think and think, S-I-N-K, are very similar by all accounts, but kids don't do that. So the analogy force has got to be very weak when you learn words. So, this is not, it didn't seem right to me in the beginning, but if you look at the facts, that's what
you look at the words you already have in some classes split by this kind of rules, where these kind of rules seem to be kind of unnatural to me, because I just don't see how I can put catch with bring in the same class. I will not make that kind of analogy.
It's not clear that the second language learning problem is the same as the child language learning problem.
And it would be very interesting to try to collect these data for second language speakers. You might very well get a different,
Right.
I mean, second language learners. You might get a
There's
different analogy.
another issue that is, whether the way you learn words is the same way you produce words or use the words. I mean, I don't know, but I only know this acquisition case, and it seems fairly clear to me. But that's a good point. You should look at it second language learning.
I mean, this particular difference, I think, has been claimed, although I can't
Right. I mean,
follow the citation.
What seems natural, doesn't really mean anything, right? I mean, we really have to look at what's going on. Yeah. There's another question?
Yeah, well, a question. It looked like from the child error data that the rate of errors on irregular words was based on the output form, the past tense.
Right.
The class of, say, bought and caught instead of catch and buy. But you're talking about evolution happening, and I guess your learning happening based on the math between the present and past tense. Like, evolutionary analogy happens on the present tense.
Evolution, well, the analogy there is for any kind of process that it doesn't have to work on phonography. It can work. The learning algorithm can work on any sort of input-output mapping. It doesn't have to be phonography. It doesn't have to be past tense. It can be nouns or something. So I mean, I don't.
It just sounds like they're two. Like you're saying that the output, the error rates for the children are based solely on the probabilities of the past tense stuff, whereas the evolution happens based on surface form resemblances in the present tense. So those are two different.
To me, I don't think the force of I don't think surface form matters all that much. I mean, the surface similarity matters, very much. Then we'd be expecting a lot of think-thunk type of errors. So if you just get rid of, forget about similarity altogether, you simply hear a thing and you hear a word and you hear a pattern, you make a link between the two. It's simple enough, and it seems to be quite compatible with the acquisition data. So I don't see the role of analogy. I mean, there is a role of analogy, which is exactly as big as 2%. Yeah. Well, yes, Jason.
There's work that's kind of related to the last part of your talk, but I'm having trouble remembering whether it uses rules at all. Luke Steels has done some stuff. So I was just going to ask you to comment on that work if you knew it and its relation to this.
No, I don't.
Okay, well then I won't summarize it.
Yeah.
I have two questions. The first was about, what you take to be the empirical status of the so-called U-shaped curve, and whether you take that to be a good description of what actually goes on, or at least a partial description.
Right.
And if you do take it to be true, then it's not clear to me how that would follow from your system.
That's a very good question. They empirically, from a developmental point of view, at least for this case, there's no strong evidence for U-shaped curve. Painter, in one of his more popular writings, actually give a U-shaped curve for Adam. But if you look at the data for the other three kids, they actually not U-shaped curve. Okay, so, but I believe U-shape is probably there, but kids already gone through that stage by the time they're producing these things. Because from this learning point of view, remember in the beginning you do memorize things, by rote.
Right.
So you can probably say that if you haven't seen enough rules of enough words that would give you the default rule, you may just have a list of pairs.
Right. But what I'm wondering is what would actually force you, if the U-shaped curve is a description of some phenomenon that falls under the domain of this algorithm, what would give rise to that? I mean, it seems to me that what you need is something like what the Rumelhart and McClellan model needed to get the U-shaped curve, namely to be pummeled with lots of diverse regular forms, and that would lead you to sort of overgeneralize the application of that form. I mean, if you're just faced with this and you're trying to sort of extract information from the evidence, it's not clear why you would ever overgeneralize in that way.
Well, before you get the default rule, there's no other rule that's going to apply. So there's no competition, right? But only when you get the default rule, there's actually you suddenly have a compounding factor. You can be stuck into the default rule. But before it happens, you don't have it.
But you presumably don't get the default rule without also getting the irregular rule. So I mean, the arguments that people have made, people I think are making, where it's sort of a different quality that you sort of, the old view was that you learn the default rule and then the other stuff you just pick up afterwards, and that's why the default rule kind of takes over, because you haven't learned all the other fine details. But it seems to me that since you're sort of starting with these very specific rules, and you have to be forced to this kind of very general default rule, it's not obvious why you would over-apply a very general rule at any point. Does that make any sense?
I guess that depends on how, relatively speaking, how fast the irregular rules and the regular rules are learned.
Right. So in other words, it depends a lot on the distribution of the
Right,
input
right,
to the
yeah.
child.
Yes.
Right.
Right.
So
yeah.
Sorry to choose from. Well, so you have shown that some of the irregulars are actually aided by essentially getting a free ride on the kids' knowledge of phonology, so that's why those specific irregulars are learned faster and so forth. So the question then, as you may expect from me, is why is it that phonological regularity is excluded in the morphologically regular cases? So why don't you get beat bet, keep cap but beat beat? So what you have shown us was that phonological regularity is now sort of cut off from the domain of the regular, morphologically regular past tense.
There seems to be some principle of conservativity going on. That unless kids see the instance of association between between a verb and a rule, it won't make that jump, even in cases when the analogy seems to be strong.
But why are the data what they are?
The data are because they've seen instances of say of lose lost, and it seems like upon quite a few, probably not so many exposures, because if you go back to the slide here, you can see if this story is correct. Upon seeing 13 or 14 samples out of 100,000 sentences, is going to make the child very reliably associate a word and a rule. So
but you have shown us that those things are not specific to items. You said that they are general process of English.
Right.
So why is it that they're excluded exactly in the domain of regular past tense? So there is one regularity which is excluded from the domain of some other regularity. So you have complementary distributions of regularities.
Is it irregularity referring to vowel shortening?
Vowel shortening.
Okay. Is included in what?
It's excluded in whenever you put the regular past tense, it's excluded.
Right.
So you have beat, it's the same context as kept, and beat doesn't give you bet.
Right.
Despite the fact that the vowel shortening is a regularity of English, as you've indicated.
Right. That's a good point. I never actually thought about it. So let me see.
That's my argument against Pinker, that if you had a dual root
Right.
system, you'd segregate the regularities on the same root and the irregularities on the other root. But what you find is that the
Right.
two major regularities, phonological and morphological, have complementary distributions. So doesn't help you to have one group that's dedicated to regularity.
Right. Maybe they are, you know, organized in different places. If we want to go there, right? Right. Yeah. But that's the point. Yes.
So in your talk, you posed this as kind of a generation problem, but in a sense, for children, it's really a recognition problem, where they really don't necessarily know what the past, what the present, and what the past tense forms are to start with, and so now they don't necessarily know that lose and lost are connected. So it might be when you pose it as the recognition problem, the point of these rules actually becomes more clear, because once it's in terms of the recognition problem, they can detect these regularities more easily because they've seen the rule more frequently. And that way you get kind of away from, I think, what Dr. Berzio was referring to, because you don't have to kind of come up with you don't have to pose new irregularities, because the only thing you're trying to do is find the best generalization to the data you've already seen and understand it. I don't know if that's does that.
Sure.
Okay. Anyways, but that kind of fits in with the
It's interesting take this.
conservative.
Anything else? Oh, yes.
Well, I have a silly question. I don't understand why people don't try to remove this irregularity, these special cases from the language.
I'm sorry?
Why people over time don't try to remove the irregular?
You know, because people are strange animals.
Well, as far as I know, Chinese government try to do that similar things. If for some special characters, most of the people use the wrong pronunciation, then the government will declare that this character is correct pronunciation. It will change the pronunciation. And I think, well, for those stuff, this irregularity in English, I think it's just, it has no meaning for the language. It adds no more beautiful or no more meaningful to the language. It just
Keeps us in worse distance. Evolutionary logic.
I don't know what the situation in China is like. Do I understand that the government declared something about language?
Yes.
Yes, well, in Czechoslovakia under communism, they declared various things in orthography, and it was totally unsuccessful. I mean, it just made, nobody, the party newspapers would follow it, but it would look so ugly that nobody would. And it's back to what it used to be. I mean, without any declaration, it just.
That's why I look at kids, because kids haven't. That's why I look at kids, because kids haven't been polluted by social cultural values. So they do what they're, they do what they're. They do what
I really felt very strange because when I was young, I was really. I don't like those special cases. They often exams and brought me troubles.
I mean, those are 2-year-olds, right? Those are 2 or 3-year-olds. They don't have exams.
No, I mean, we can get the Americans to follow the metric system, so there is no.
Yes, absolutely. That's right. Yeah, I mean, you're right. If that's the case, then I have nothing to say.
You did have a story about that, though. Your perspective does shed light on the irregularity, unlike the Hallett perspective that says, well, you're saving memory. Well, if all you were doing was to save memory, then indeed we should get rid of, just one rule would save a lot of memory, more than having several. But your approach does help, because when you throw in the statistics and so frequency gives a special status to items, and so makes them more resilient to the pull from the regularity. So that's the trade-off.
Yes. I mean, in principle, you can even, in the equation of the decay, or how often you're going to, get, how often you're going to lose your irregularity tag, you can add some, social factors to it. I mean, I don't, making the system more complicated in principle.
I can take one last question and then.
No. She was going to contribute by not asking.
By not asking, okay. There might be another class meeting here at 6, so we should.
Okay. All right. Thanks very much.